In this module, we will look at the engine oil system, including the system flow. Next, we will look at the fuel supply system. Finally, we will take a brief look at the electronic engine control installed on each engine. The engine oil system provides lubrication of engine bearings and gearboxes, as well as supplying oil pressure for propeller actuation. The oil system includes an oil sump with a sight glass that is integral with the compressor case. The oil is stored in a 14.4-liter tank, which is integral with the rear inlet casting. A pressure regulator maintains a system pressure of 55 to 65 psi. The tank has a filler neck with a cap, a pressure strainer, and scavenge chip detector. Oil quantity is checked by a sight glass or a dipstick. The single system supplies oil to the reduction gearbox and the turbo machinery. The oil system is composed of two subsystems: the pressure oil system, which supplies oil to the engine, and the scavenge oil system, which returns the used oil to the tank. A gear pump driven from the accessory gearbox pressurizes the oil system and routes it to an oil cooler. From the oil cooler, oil is routed through a pressure filter and then to an engine lubricating network. Oil is also supplied to the reduction gearbox lubricating network. The engine network provides oil pressure to the fuel heater, oil low pressure switch, oil pressure transmitter, oil temperature sensor and accessory gearbox, and engine bearing cavities. The oil low pressure switch for each engine illuminates an Engine 1 oil or Engine 2 oil warning light, respectively, when the associated engine oil pressure drops below 40 psi. This will cause both master warning lights to flash and a CRC will sound. There are two different alerting systems for oil pressures of less than 40 psi. The low oil pressure warning on the crew alerting panel monitors the oil cooler outlet for low pressure, but is inhibited for 30 seconds during engine start and at all times when the associated condition lever is in fuel shutoff. A separate transducer signals low oil pressure with a red light on the oil pressure gauge. This light is also inhibited when the associated condition lever is in fuel shutoff. The oil temperature sensor provides oil temperature information to an oil temperature indicator located on the flight instruments panel. The oil cooler mounted in the rear of the engine intake duct controls oil temperature. A flap valve located in the nacelle automatically controls the airflow over the air oil cooler. If the oil temperature is greater than 81 degrees Celsius, the flap opens and the oil is routed through the oil cooler. The cooler is then progressively bypassed as the temperature approaches 71 degrees Celsius. In the event a clog develops in the oil cooler, a valve will open to allow oil to bypass the oil cooler. The pressure oil spur gear oil pump is mounted in a pack on the right side of the rear inlet case. A pipe from the oil tank is connected to the inlet side of the pump. A second pipe from the outlet is connected to the remotely mounted air cooler. A low oil temperature relief valve returns the oil to the tank to prevent a pressure surge during cold starting. From the cooler, the oil flows to the pressure regulating valve and the pressure filter. The pressure regulating valve maintains constant oil pressure in relation to the air pressure in the cavity. If the oil pressure overcomes the air pressure, the valve opens a port to return oil from the main pressure line to the oil tank. The pressure filter also has a bypass to ensure adequate flow if it becomes blocked. From the filter, the oil flows in two directions. Oil flows to the reduction gearbox through the fuel heater and the fuel-cooled oil cooler. The fuel-cooled oil cooler is mounted on the reduction gearbox. An oil pressure transducer is located downstream of the pressure filter. This transducer supplies oil pressure information which is displayed on the oil temperature indicator on the flight deck. A pipe carries the oil to the auxiliary oil tank. The auxiliary oil tank is pressurized and is always maintained full of oil. Oil from this tank flows by internal passages and pipes to the electrical auxiliary feathering pump and to the propeller valve module mounted on the reduction gearbox. The PVM uses an electro-hydraulic valve to meter oil pressure to the propeller pitch change mechanism. Oil from the tank is also distributed through internal galleries to the reduction gear train and bearings. Oil for the turbo machinery main shaft bearings and accessory drive gears and bearings flows from the pressure filter. Nozzles direct the oil at the 7 main shaft bearings for lubrication. Reduction gearbox scavenge oil drains into a cavity in the bottom of the gearbox. A chip detector is installed in the gearbox cavity. A scavenge pump, which is part of the pump pack on the right side of the rear inlet case, draws the oil through a pipe on the left side of the front inlet case. The pipe is looped upward to prevent the gearbox oil from flooding the oil tank when the engine is not running and is connected to an internal oilway in the front inlet case. This oilway aids in anti-icing of the intake. From the inlet case, The oil flows through a pipe to the scavenge pump, through the scavenge filter, and to the oil tank. The scavenge filter has a bypass valve in case of filter blockage. Oil from the accessory casing and the number 1 and 2 bearing cavities is scavenged by gravity. Oil drainage from the number 3, 4, and 5 bearing cavities is gravity-driven and is assisted by air leakage from the bearing labyrinth seals. Oil from the number 6 and 7 bearings is scavenged by a pump, which is part of the pump pack. Now we will look at the fuel system. Fuel for engine feed is drawn from the feeder compartment and is delivered under pressure to the hydromechanical unit, or HMU. Fuel flows through the fuel heater prior to entering the HMU. Each engine fuel supply is heated and filtered before entering the engine-driven fuel pump. The filtering and heating occur in the fuel heater. This unit transfers heat from the oil to heat the fuel through a heat exchanger. Fuel temperature is thermostatically controlled. If the fuel filter is restricted or blocked, the fuel will bypass the filter to supply the engine. After the fuel heater, the fuel is pressurized by a high-pressure pump which then supplies the hydromechanical unit. This high-pressure pump incorporates an additional fuel filter. Clogging of the filter is indicated by the illumination of the fuel clog light on the center flight instruments panel. The hydromechanical unit, or HMU, performs two functions. The first function is to deliver fuel under pressure to the engines. This delivery mechanism is controlled by a metering valve assembly. Any excess fuel is returned to the high-pressure pump inlet. The second function of the HMU is to provide the high-pressure motive flow required by the fuel tank jet pump. Fuel flows through a motive flow valve. Fuel flow is sensed after the HMU. The fuel flow is indicated on the associated fuel flow meter. Prior to entering the engine, the high-pressure fuel flows through a fuel-cooled oil cooler. This cooler uses engine fuel to cool the oil used by the engine's lubricating system. After the fuel-cooled oil cooler, the fuel flows through a flow divider which supplies fuel to the engine fuel nozzles. Normal control over engine operation is through the scheduling of fuel flow by the electronic engine control installed on each engine. The EEC, acting through its associated HMU, controls fuel scheduling in response to inputs received from the power levers, the power management selector, and the bleed position. In addition, engine sensors provide engine and propeller speeds, engine torque, and ambient conditions to the EEC. Ambient conditions are supplied to the EECs by one of the air data computers. The ADC source is selected by the ADC switch on the left side of the center flight instruments panel. This switch also controls the source of ADC data that is supplied to the Flight Data Acquisition Unit. The ADC fault light illuminates in the event the ADC data source and the switch position disagree. The HMU may also be operated in a manual mode should EEC control not be available. Control over EEC fuel schedule modes is provided by engine EEC push buttons on the instrument panel. There is one push button for each EEC. When an EEC push button is pressed in, the associated EEC is operating and is adjusting the HMU fuel schedule through the stepper motor. This stepper motor actually slightly decreases the fuel flow commanded by the HMU. No lights are illuminated when an EEC push button is pressed in, as this is the normal push button position. When an EEC push button is released out, the associated HMU is in sole control of the fuel schedule. The HMU will schedule fuel based on power lever angle. The off caption illuminates when the push button is released out. The fault light illuminates amber when the associated EEC fails. This will trigger a CCAS warning which consists of a single chime, both master caution lights flashing, and the illumination of the engine light on the crew alerting panel. When an EEC failure occurs, the associated engine power will be frozen at the pre-failure value. When the failed EEC is deselected by checklist action, the HMU will revert to base law. This concludes the engine oil and fuel system.